Now let's solve one more question. Show that the number of equivalence relations on the set 1 to 3 containing 1 2 and 2 1 is 2. Now to solve this question, first of all, we'll find the Cartesian products of A and A, that is A cross A. Now here A cross A is equal to 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2 and 3 3. So you can see in all there are 9 ordered pairs. Now a relation on 1 to 3 will be reflexive relation if it contains 1 1, 2 2 and 3 3. So this relation must contain 1 1, 2 2 and 3 3. And now 1 2 and 2 1 has also to be a part of this relation. So the new relation becomes R is equal to 1 1, 2 2, 3 3, 1 2, 2 1. Now here 1 2 is present and 2 1 is also present, so it's symmetric. Similarly, 1 2 and 2 1 are present, then 1 and 1 is also present. So this relation is the equivalence relation. So the shortest relation containing 1 2 and 2 1 on the set 1 2 3 is R is equal to 1 1, 2 2, 3 3, 1 2 and 2 1. And in the A cross A, so you can see we are left with 4 pairs. Now let's add any one of them. Now suppose we add 1 3. Now if we add 1 3, then we shall also have to add 3 1. Then only this relation will be symmetric. Also now we have added 1 3 and you can see 2 1 is also present. So if 2 1 and 1 3 are present, then we must also have 2 3 because this relation is transitive. So now we shall have to add 2 3. And if we have 2 3, then we must also have 3 2. Then only this relation will be symmetric. So now you can see we have added all the ordered pairs from A cross A. So now you can see if you add any other pair of the 4 unleft ordered pairs, then for this relation to be equivalent, we shall have to add all the 4 ordered pairs. So the other equivalent relation containing 1 2 and 2 1 on set 1 2 3 is the universal relation on the set A. So the number of equivalence relation on the set A containing 1 and 2 is 2. Let's solve one more example. Prove that the relation R on the set Z of all integer numbers defined by xy belongs to R if and only x minus y is divisible by n is an equivalence relation on Z. Now let's first check it for reflexivity. Now this relation will be reflexive if A is related to A. Now as per this relation, if A and A belongs to R, then that means A minus A should be divisible by n. Now A minus A is equal to 0 and 0 is always divisible by n, where n is integer. So that means AA belongs to R. So that means the given relation is reflexive on Z. Now let's check whether this relation is symmetric or not. Now this relation will be symmetric if AB belongs to R, then that means BA also belongs to R. Now if AB belongs to R, then that means A minus B is divisible by N. Now if A minus B is divisible by N, that means A minus B is equal to N into P, where P is an integer. Now A minus B is equal to NP. Now let's check whether BA also belongs to R. Now BA will belong to R if B minus A is also divisible by N. Now B minus A is equal to minus N into P, or we can say it is equal to N into minus P. Now B is related to A if B minus A is also divisible by N. Now B minus A is equal to minus N into P, or N into minus P. Now P is an integer, that means minus P is also an integer. So B minus A is also divisible by N. That means B is also related to A. So A is related to B, then B is also related to A. So that means given relation is symmetric. Let's check whether this relation is also transitive or not. Now let ABC belongs to Z, and suppose AB belongs to R and BC belongs to R. Now if AB belongs to R, that means A minus B is divisible by N, or we can say A minus B is equal to N into P, where P is an integer. And also BC belongs to R, or we can say B minus C is equal to N into Q, where Q is an integer. So we have A minus B is equal to N into P, and B minus C is equal to N into Q. Now suppose we add both the equation, then it becomes A minus B plus B minus C is equal to NP plus NQ, or A minus C is equal to N into P plus Q. Now P and Q belongs to Z, then P plus Q also belongs to Z. So P plus Q is also an integer. So A minus C is equal to N into an integer, or that means A minus C is also divisible by N, or we can say A is also related to C. So if A is related to B and B is related to C, then that means A is also related to C. So given relation R is transitive. So now given relation is reflexive, symmetric and transitive. So that means this is an equivalence relation. Let's try one more question. Let R be the relation over the set of all straight lines in a plane such that L1 is related to L2 if and only L1 is perpendicular to L2. Then state whether R is symmetric, reflexive, transitive, or an equivalence relation. Now let's first check it for symmetric. Now this relation will be symmetric if L1 is related to L2, then L2 is also related to L1. Now L1 is related to L2 only when L1 is perpendicular to L2. Now if L1 is perpendicular to L2, that also means L2 is also perpendicular to L1. So that means L2 is related to L1. So this is a symmetric relation. Now let's check whether this is reflexive. Now this relation will be reflexive if L1 is related to L1. Now L1 is related to L1 if L1 is perpendicular to L1, or L1 is perpendicular to itself. But no straight line can be perpendicular to itself. So this is a false statement. Now check whether this is transitive. Now if L1 is related to L2 and L2 is related to L3, that means L1 is perpendicular to L2 and L2 is perpendicular to L3. Now is it that L1 is also perpendicular to L3? No. In fact, L1 will be parallel to L3. So this is also a false statement. Now is it an equivalence relation? For a relation to be equivalence, it should be symmetric, reflexive and transitive. But it is neither reflexive nor transitive. So this is not an equivalence relation.